Hello. Hi guys, good morning. I'm new to the studio. We problem of finding critical and pseudo-critical edges in Williams spelling tree. For sure, a bit spoiler. If you want to know the entire intuition, please skip the next 5-20 seconds. But if you want, then we will see entirely what is DSU, what is a MST, and how to solve this problem. We will see everything. If you don't know MST, DSU, no worries at all. Just watch this video. Cool. The question says that okay, I'm having an undirected connected graph. For sure, the graph will always be connected, which means no node will be outside the component. Cool. I have n vertices. Naming as 0 to n minus 1 nodes and an array of edges where each edge I represent by u, v and a weight between those two edges. So if I say an edge, it connects ai, it connects bi with this weight called as w or weight of I. Now it represents a bidirectional and weighted edge. So for sure, if it's an edge or undirected graph, so it's a bidirectional edge. Nodes ai and bi, between the nodes ai and bi. A minimum spanning tree, MST. If you don't know what is MST is, I'll explain what MST is. But yeah, a minimum spanning tree is a subset of graph edges which connects all vertices without a cycles. As the name says, minimum spanning. Minimum as in the tree. The minimum spanning tree. The tree which is made should have the minimum weight as total sum. So if I span the entire tree and collect the weight of all the edges in that tree, so it should be as minimum as possible, and that is the minimum spanning tree. We will see what it is, but more elaborated by idea. The word itself says what's a minimum spanning tree. Cool. And with the minimum possible total weight edges. So first question is what is an MST, and it just says minimum spanning tree. If I have a graph, I need to make a tree out of it, and in that tree should have the minimum weight. It should have the minimum weight possible. As you can see, if I choose and see when I represent this graph, I have indexes. The first one is the indexes, and Aryan, how to the indexes? Simply, if I just iterate on the edges list, you will see that the first edge I represent by ai, bi and weight of I. ai, bi and weight of I. So ai, which means 0 to 1, is just ai and bi, which means ai and bi. The weight is actually 1, but as it is a first edge, so I just indexed it with a 0. And same I will do for every edge, and that's how I represent my actual graph. Now from graph to make an MST, what I did was I just chose some edges such that the collection, which means the sum of weights, is actually as minimum as possible. So you will see the weight is actually 7, which is as minimum as possible, and also the tree form, the graph form is actually a tree. So that's the reason I will get a minimum spanning tree. So first thing I'll choose the minimum weight so that I will form a tree. And you know the property of a tree, it is nothing but if I have n nodes, I will have n minus 1 edges exactly. You will see I have 1, 2, 3, 4, 5 nodes. So I had 1, 2, 3 and 4 edges. That's how you make a tree. So now again, let's say if it is another MST, again, it's just that it will also satisfy the same property. The weight will actually be the minimum, which is actually 7. So the weight will actually be 7 of his graph also, and also it will be a tree. So our condition is to make an MST, I should take all possible minimum weights, but if I am taking those weights, I should also consider that okay, I should form a tree and not a graph, which means it should have n minus 1 edges. Now we know what is an MST. Now what our task is to find the critical and pseudo-critical edges. Now what is Aryan the pseudo-critical edges? It's the main part. It's very confusing to understand, so please understand it very carefully. Now critical edges, it itself says critical edges are nothing but an MST edge whose deletion from the graph would cause the MST weight to increase. It's called a critical edge, which means the deletion, which means if I delete, or which means if I exclude that edge, so MST weight will increase. If I and we'll see, but yeah, please understand this crux. If I exclude that edge, the MST weight, which means I will exclude that edge. Now I will try to make an MST again. So the weight of that tree will actually increase. So that will be a critical edge. Now what is a pseudo-critical edge? Pseudo-critical edges is that which can appear in some MST but not all, which means it is not important if it occurs or not occurs, it will still give me a MST as the minimum weight, which means either if I include it or I exclude it, no worries at all, MST weight will still remain the same. Here I saw I excluded it, the weight increased. But here, if let's say the weight remains same, and if I let's say include it, I purposely have to include it, and still the weight of MST remains same, then for sure it's a pseudo-critical edge. If see again, if I exclude it and the weight increases, which means it's a critical weight. Here it says, even if I exclude it or include it, no matter what, if the weight remains same, it's actually a pseudo-critical edge. Now coming back to, okay, like we know what it is. Actually, we will see by the entire diagram and stuff. But meanwhile, we had known what is an MST. It's just that property of MST that for sure, firstly, the weight should be as minimum as possible. And another thing is that it should form a tree. So if you are, although to grab the minimum weight possible the entire tree, I will just firstly, it's very intuitive to just go greedily, which means always grab the minimum weights and try to attach the nodes. But as I am grabbing the minimum weights and try to attach the nodes, what if a few nodes are already connected, but still, shall I take the minimum weight? No. I will take the minimum weight only when it is actually forming a tree, which means actually attaching two non-connected components. Cool. That is how we can form an MST. But again, that's the main task. How to actually form an MST. Although verbally we have explained, okay, we will just grab the minimum weights and then we will try to form a tree. But how? How as in, see, we have two algorithms to form a minimum spanning tree. One is prims, next is Kruskals. The way we define intuitively, as we saw, okay, we can grab the minimum weights and then we'll try to form a tree. That is actually a Kruskals algorithm. That's the reason we just go with the Kruskals, because it's more intuitive. As the way we spoke of, that's the actual stuff which we will implement. Now, again, the same stuff we will do. But how we will do, okay, we will take all the minimum possible weights. Now to take the minimum possible weights, if we want the entire tree weights sum to be as minimum as possible, so for sure, take the individual smallest weight possible. So what I will do is I will sort all the weights in ascending order, so that I will start taking those weights in the ascending order itself, which means minimum weight I will take first, then bigger, then bigger, then bigger, and so on and so forth, so as to get the minimum possible sum. But while taking the minimum possible weight, which means let's say so far I have just grabbed this entire graph, this entire stuff I have been making by grabbing the minimum weights and just attaching those between two nodes. Next, let's say I encounter this next node having a weight as 8 and here the weight is 9. So I will ask you, shall I use this edge of weight 8 or shall I skip it? Now I will say, if I am going to use this edge of weight 8, it is not making a tree, it is actually making a graph, because it's actually, you will see it is not connected, it is already connected. If it is already connected and if it is just one disjoint set and I am again making an edge in it, so it will not impact me. So what I will do is I will just ignore this, because it was already in this connected component. It was already in this connected component, which means making this edge will not impact. My tree will always be there. If I just ignore this and not use at all, my tree will always be there. So why should I use it? I will not use it. So I will go to the next node. I'll go to 9. Even still, see, even if it was bigger, but it was just not actually, like, it is actually impacting my tree to be made. Now I will make my entire tree, which means I just connected two disjoint sets. That is, you will only use a edge of some XYZ weight. Firstly, you will start using the edges in the weights in the ascending order of their weights. Now, if I encountered a weight of 8, an edge of weight 8. Now I'll encounter a edge of weight 9. So I got an edge of weight 8. I will not use it because it was just connecting already connected components. So I will not use it. Now, Aryan, how to know if it is connecting existingly connected component or two different component? Nothing. Here you just had an option. This edge of weight 8 was connecting A and B. So I'll just go and ask, hey bro, are A and B in the same connected component? Now the fastest algorithm to know if two nodes are in the same connected component or not is nothing but a union find by rank, or like union find, or it is also called as is join, set, union, or as DSU. So by this, I will just get to know. I will just ask what is the just find A and B. If they have the same parent, for sure they are in the same critical component. Now you say, Aryan, what's a parent? What's all this stuff, DSU and stuff? No worries, we actually see it, but yeah, just have a quick idea, okay? It will just go and see if these A and B are in the same critical component, and how it does it. It will just, when I'm actually connecting these nodes, I'm actually making a parent out of all of these, which means this node will have a parent A, this again will have a parent A, it will have a parent A, it will have a parent A. So I will go and ask, what is your parent? What is your parent? It will say A's parent is A, B's parent is also A, which means parent are same. If the parent are same, they are in the same connected component. Now I will just go and ask C. Your parent is C. Cool. The parent are different, which means they are in a different connected component, and that's the fastest algorithm to know, okay, if they are in the same connected component or different. If it isn't different, simply you can now use this particular bit, because now you're actually making a tree out of that particular two components, because just attaching two components, which means, see how you make a tree. It's just that, okay, you just attach two nodes, you just attach two nodes, you just attach two nodes, you just attach two nodes. Now if I just ask you, if I have this node, if I have this, I attach two nodes. Now again, this is one component, this is another component, right? This is another component. Now to just simply attach it, I'll simply attach, I can attach this, but I will not attach this because it was already attached. It was already a component entirely. So I'll just attach this one. So as to make a tree. So I should know at any point of time if they are in two different components or same components, and that I can easily, and fastest way to find out is nothing but a DSU. Cool. Now we know how our Kruskals will work. How with the help of finding union find or a set union, I can go and find if they are in the same component or not. If they are in the same component, I will skip that particular edge weight. If they're in the different component, I will go and use that edge weight, and I'm using the edge weight on the basis of the ascending order. Now you know everything about what is actually gonna be MST and how we can actually implement the MST. Now coming on back to how and what we have to do. Again, we have to find the critical and pseudo-critical edges. Now as we have said, critical edges is nothing but we have to include it. We have to include it, which means if we exclude it, the weight of MST will increase. So I will just do the same thing. We are actually Indians. What we will do is we just try the opposite. What we do is we try to exclude stuff. Now after excluding, now I am saying, okay, I have to include it, which means I'll try excluding it. If excluding it increases the weight of MST, which means, oh, I should have already included it. Right? So that's the same stuff. To know if an edge is critical or not, I will exclude it and we'll see if my MST will increase or not. And Aryan, how to exclude it? Simple. I will just say, although I'll show you, but still, I'll just say, okay, never use this particular edge in my entire MST and now make my MST. If you are able to still find an MST with the same weight or as out of original MST, now when I say MST, I always mean the weight should be as minimum as possible. Now when I say it affects, which means the weight of the new tree formed, as I wanted to make an MST, see, as I wanted to make an MST, if I just make an MST out of this graph, it will always give me an MST of weight 7. It is the actual original MST. Now if I just remove this edge and consider, okay, I am just blindfolded and I can't view this edge, which means I cannot use this edge. Now I will try to make an MST out of this new graph, right, with these all edges. Now if the new MST is still 7, so for sure it didn't affect me. But if it actually increases, let's say it becomes 8 or 9 or anything more, which means, oh, removing this edge actually impacted my MST, new MST, right? So that's the reason I will just try to exclude this particular, and still, please don't worry, I'll actually explain by removing actual edges. If I want to find the critical edges, I will just try excluding it. If after forming a new MST, Aryan, so you will try for every edge. Yeah, I will try for every edge. I will try to remove every edge and see if it's actually impacting my entire MST or not. Aryan, which means for every edge you will apply Kruskal's algorithm again and again to find the minimum spanning tree. Yeah, I will. Why I will? Because you know the constraints. The constraints are not that big. If we just go and look at the constraints, where are they gone? Cool. You will see the edges are nothing but just 200. So for sure, for every 200 edges, I can go and apply a Kruskal algorithm again and again, because I know Kruskal is nothing but O of E log V. Again, no worries on the complexity part. We'll actually view that again later. But yeah, excluding it and then seeing if it affects or not, which means I just find the new MST after excluding this edge. Now, to find if it's a pseudo-critical edge, my task was either if I included or excluded, it should not affect, which means the weight of the new MST should be actually equal to the original MST. I know the original MST I have already found. I have excluded it, which means I have tried excluding it. I know what is the MST. Now, I have excluded it. I will use the exclusion and I will just only include it now, because I know the new MST after excluding is this one. After including, I will know if, like when I say including, I mean I have to include this edge in my entire MST. So firstly, before even starting my actual Kruskals, I will just insert this edge in my tree. Now, okay, it is already there. Now start your Kruskals from onwards, because you have already included this edge, right? So I will just include this edge and I will say, now what is the MST? If the MST is still the same as that of the original MST, which means, okay, it was actually good to name it as a pseudo-critical edge. Please make sure you are actually both including it and excluding it. Both including, which means one time I included it and one time I assumed I excluded it. In both the cases, MST should remain same of the new tree formed. If it is same, then it's a pseudo-critical edge. And in this critical one, if I actually include it, no worries. But if I excluded it, then if its weights increases, then it's a critical edge. Now we just saw, okay, what's a critical, pseudo-critical, but actually let's see in actual theory, in actual practical, what it actually means. Now my original MST is actually a number 7, which means the weight of the entire tree formed is actually as minimum as possible, is actually a weight of a 7. Now if this weight is 7, I know I have to go and find for pseudo-critical and critical edges. Now for critical, you know, you will exclude an edge. So let's say for this edge, I just try to find if it's a critical edge or not, which means I will just try to exclude this edge. Now if I exclude this edge, I know I'm trying to find if it's a critical edge or not. If I exclude this edge, now what you will see, this tree is connected, okay, and this is one. So it is still not connected. So the tree is not yet formed. So still you have to either make this edge or any other edge which you can make. So you will see the only options is this one and this one to actually connect this with the entire this part. Right. So out, and I want the minimum, I want the MST. So what I will do is I'll just either, and see, you cannot use this. You can use this or this, right? And for sure this 1 and 4 are already connected, so it is of no no good to actually use this, because it's not forming a tree, it's forming a graph. So I have two options, either I can use this or this, and I want MST, so I will use the weight 2. So I'll just simply use the weight 2. Now you will see the actual new MST weight is actually 8, which means after excluding it, the new MST weight increased, which means this was actually a critical edge, which actually after being removed, it actually increased my weight. So it is actually one of the critical edges. Now again, I can go and try for another edge. Let's see if I excluded this one. So for sure, if I excluded this one, I will have another, like one of the graphs is this one and one of the graphs is this one. So I have to just connect all these two, which means that this one and this one, I have to connect these. So again, options I have is what I'm saying, I have this one, I have this one, and I have this one. Now I have to connect it. So one option is this one, but I have already excluded it. So other option is this one or this one. That's it. These are the only two options, this or this. Here I want the MST, so I'll choose this one, minimum weight. So I just choose this one, minimum weight. Still the new MST weight is actually a 8. So again, it is a critical edge, because after removing it, I increased my MST weight. Again, next example, let's say if I choose it. Now to choose it, I will first check if it's a critical edge or not, which means if I just excluded it, again I will have one of the component as this, another component as this. If I have these two as a component, if I have these two as the component, you will see back again a triangle which means I have one component as this, another component as this. I just say, okay, I will exclude this edge. So options with me remaining are this particular one, and this one, and this one. Again, minimum 2, 3, and 6. Minimum is 2. So I'll just use this particular 2. So I use this particular 2. Now I'll use this 2. Now the MST formed is actually a 7. Oh, excluding it, it did not increase my MST. For sure, it is not a critical edge, but I need to also check if it is a pseudo-critical edge or not. So in excluding, I checked. Now I will check. I will for sure include it, and we'll see if it's actually impacting my MST or not. So you will see this entire tree was already made by including this particular edge. So for sure, including it was actually giving me a MST, because you know it's already MST, and it's actually also including it. So it's actually a MST because the weight is 7, which is the original MST weight. And that's the reason I can just simply say, okay, it's an actual MST, or it's actually a pseudo-critical edge. Again, for this also you will see it's actually included. So I tried excluding it, weight remains same. I tried including it, which means including it, for sure including it, weight remains same. It's a pseudo-critical edge. I tried excluding it, weight increased. Oh, it's a critical edge. Cool. That is how you can simply solve it. And now, just having a code for you, a pseudo code to actually understand what we have to do in this entire problem. Firstly, our main task is to actually know and find the MST of any particular weight. But considering what I have to give on runtime command as if I want to include an edge or I want to exclude an edge. So that's a primer thing. Although to get an MST, I just want what are the number of nodes and the edges, which means the entire graph I need. This edges is actually the input of this entire problem, which is actually nothing but node AI, BI, and the weight of I. That is nothing but edges, which I have for every particular edge I have, and that's the number of nodes which I have. That's an input for this problem. But the special part is nothing. Okay, I need to exclude an edge and include an edge. So I'll just have this as an argument as well, so as to know, okay, if I want to include an edge in my MST or exclude an edge in my MST. So that's nothing but edges, or you can say that edges indexing, or nothing but edges numbers. Now, this MST will actually return me the minimum spanning tree weight of this entire particular graph which I make. Now, okay, it's a function which I will just implement by Kruskals. I'll explain the entire function when I will go into the function itself, but yeah, it's an MST question. Now, the main task of this algorithm was to firstly push back the indexes in the edges vector. Now, you can just maintain the indexes any way whatsoever, but I know that what we have to return in this entire problem was actually the indexes. These 0, 1, 2, 3, 4, and 5 are the indexes of these edges. So what I will do is I will just push back a 0 in this. So, okay, the 0th index of this particular vector will say I am a AI, it will say I am a BI, it will say I am a weight, and the next vector or the next element of this particular vector will say, okay, I am the index. So I want indexes, so I will just simply push the indexes firstly in my edges vector. Now, I know that to actually start my Kruskals itself, I need to sort my entire edges on the basis of their weights in ascending order. So I will sort the edges in the ascending order of their weights. Now, I have to get the original MST so as to before start applying or removing or excluding any edges. So I will just get the original MST, which means MST of this entire graph, which means the minimum spanning tree of this entire graph without even excluding, including any, without even putting any condition whatsoever. What is the original MST of this entire graph? I'll go and get the MST. I'll just give these two, excluding, including, not required, because I want the MST possible whatsoever is there. It is the original MST. Now I will just go and try to find if an edge, if it's actually a critical edge or a pseudo-critical edge, which means a critical edge, if it's there, okay, it's there, but another edge, it is a pseudo-critical edge or not. So what I will do is I will just go and iterate on all the edges of this entire graph, because for every edge I will go and find the Kruskals. So firstly, I will just check for if I exclude it, which means if I just say, oh, I'll not put this, I'll exclude this particular edge. So I'll go and say in my MST, get the MST, and NE will remain same. But right now I'm saying the edge right here, I will exclude this edge from my entire MST, and I will get the new MST, which means the new weight of this entire MST. Now, as I'm saying, okay, I'll exclude it. So I'll just make sure, okay, whenever I'm grabbing and I'm running my Kruskals algorithm, which means I'll just go on the edges in the order of their weights. I just include it on the basis if they are in the a different components, all that stuff. So even if both the components are different, still it's time to attach that particular components. Still, if it's actually marked as excluded, so I'll just simply continue, skip that particular edge. So, and for sure include has no condition, so I'll just have a -1 for that particular thing. Now, if the new MST weight, if it's actually more than the original MST, which means for sure excluding it hampered my MST weight. If it hampered, so it was a critical edge. Now, if not, okay, if not, which means if it goes down, which means, okay, if I have tried removing, which means if I have tried excluding that particular edge, now, if it just goes down, which means, let's say the new MST weight is same as that of original MST, so it will not go here. It will try to go in the next else if. Now here I excluded it. Now I will try to include it. Now excluding it was for the critical one, but excluding and then trying for including was for pseudo-critical one. So for pseudo-critical, I have to try for exclude also and include also. But for critical, I only have to try for exclude. Right? So I'll just go and try include the edge, which means I'll just go and say, okay, bro, this edge E needs to be included for sure, no matter what. So before even starting my Kruskals algorithm itself, in the Kruskals code, I will have one liner where I will just push this edge entirely firstly, and then I will just go and try for all the edges and will go in the sending of the order of their weights and do all the stuffs. So I'll just go and include this edge and I will see what is the new MST. Now, if the new MST weight is that of the original MST, which means excluding it or including it never affected my MST weight, so it's a pseudo-critical edge, and that's how you can simply solve it. Now, I know that I went on to every edge, and for every edge I'm applying a Kruskals to find a MST, right? So that's the reason for every edge you are going to find the Kruskals. Kruskals is E log V. It's simply a O of E square log V algorithm, and space is nothing but O of E plus V as we are using in Kruskals. Now, going on to the code very quickly, I'll go and explain the entire code very deeply. Firstly, I'll explain you how actually the Kruskals is working, but before that, you should be knowing how actually a DSU works, because while in Kruskals, you need to know two components or basically two nodes, because you are connecting A and B. Now you need to know, are these A and B in the same component or not? If they are not in the same component, then only you have to connect. So how a DSU works is, it maintains a parent, as I showed you above also, as I had made this particular entire graph in which I showed you the parent of A is actually A, the parent of B is actually also A. So for every node in one component will have the same parent, and by that parent itself I can get to know, oh, if it is actually in the same component or not. So firstly, we actually go on and see how a DSU is work. A DSU, and that's it. See, I would have skipped the entire code of DSU and everything. I would have skipped the entire MST, what's an MST, how MST works, but still I went on to very deep on MST so as to actually make you understand every part. And especially, it is a code which I use primarily for DSU, and that's the best code which I could actually make out. And I have been using this code for the entire last year, and that's the only code which I use for DSU. So I highly recommend, please go and mark this code as a snippet for your DSU. If not, you can just go and watch the bar graph series as well. Let's go and walk. Let's come back. So it's nothing but DSU. Now, to actually optimize our DSU, we just have a rank concept also. So as to know, okay, if two particular components are there, which component to actually assign the parent of other component, which means if I have a very small component and a very big component, right? Okay, if I have a very small component and a very big component, so I should know, okay, I should assign this small component to the big component or the big to the small. So as to know, okay, if it should become a parent, so what if the small component becomes a parent, what will happen is every node in the big component needs to assign the parent as, okay, the small component's parent, right? So it is better, okay, the big component is big, like it becomes the parent and small component becomes the child. How it will help us? Because only fewer nodes will actually be impacting, and the fewer nodes will actually be having their new parent as changed. So that's the reason we have a concept of rank, so that it just optimizes our algorithm a bit. Now, higher rank is the parent. As I showed you, if a one has higher rank, it has actually saying, okay, I have more nodes with me, you have less nodes with you, so for sure my rank is higher, your rank is lower, for sure I will become the parent of you. Higher rank person will become the parent, lower rank person will become the child. That is what we will maintain. That's the reason we maintain the rank stuff, all that stuff. Now for sure you need a rank, you need a parent, so I'll just initialize my rank and parent in this particular vector. Again, for sure every node is as equal to as its parents, as I showed you in the beginning also. Here also that, okay, every node initially, although okay, I'll show again, every node initially, as I showed you for this A, this node B. So you know, this ultimately, if they're in the same component, everyone have the parent as A. It has a parent A, it has a parent A, it has a parent A, it has a parent A. But initially when A was different, when this was different, when this was different, when B was different, everyone has the parent as, okay, A has a parent A, let's say it is C, it is D, so it has a parent C, it has a parent D, it has a parent B. So everyone has their own parent. Okay, I am the own parent of mine. But as I keep on attaching myself to other nodes, we will have only one parent to us. Now it is just the initialization of my DSU. The main function of DSU is actually to find and do a union. Now when I say find, I will go and find, are these two nodes, let's say I make as E and also F, let's say it is C, it is D. So are these two nodes E and A are in the same component or not? Or basically I can also ask B and F, are they in the same component or not? So what I will do is I will go and recursively, if still yet not I have assigned the parent of A, which means the parent of B, if it is still not assigned yet, so although while every time I do a query, let's say I ask the parent of B, it will go and ask, okay, the parent of B is actually right now D, but parent of D is actually a A's parent is actually again a A. So when I will come back and give information, I will keep on assigning, okay, A's parent is A, D's parent is A, B's parent is A. So that next time, let's say I ask B and E, what are the parent of B and E? So B has already known my parent is actually a and not a D. Because for sure, D was a actually parent, but actually the component's parent is actually a A. So that's how it just keeps on maintaining that, and that is actually helpful with the help of find. So this find will go and ask what is the parent of that particular number X. Now I will go and find the parent. Firstly, if I have to go and find the parent, I will just go and recursively ask. Firstly, I go and recursively ask if the parent, and how to know when to stop? Nothing, as I showed you, how to know when to stop, as the node and the parent both become same. So if the node and the parent both become same, you know you have to stop and you have to return that. So I will simply return that. But if not, which means, as you know, here the parent was not same, so I'll just simply keep on returning that, which means I'll simply keep on returning that. I'll simply keep on going and find the parent of my parent. So I know I have to go and find the parent of X, so I will just go and find the parent of X. But that parent of X, again I have to go and find its parent, so I'll just keep on going and finding the parent of that particular node. Here for D, I'll go and find, and how to stop? When the parent and node becomes equal, okay, it is actually the actual main parent, so please go and return that back. That's how I can find the parent of both the nodes, which means both the components or basically any node whatsoever. Again, let's say if I have found the parent, but maybe I wanted to attach these, maybe I want to attach these. So what I will do is, I know I have B, I have F. The parent of B is A, the parent of F is E. I know I have to attach both of them. If I want to attach both of them, now what? Now simply there comes is the union. So again, for union, I should know firstly if they are actually already not attached or not. So I'll again go and find the parent of both A and B, which means I'll go and find the parent of B, I'll go and find the parent of F. Let's say if I had, okay, attach, which means union B and C. It will go and union B and C, which means it will go and find, okay, what is the parent of C, what is the parent of B. Both have the same parent, which means if they are already attached. So please, if they are already same, which means if it is not same, which means if they are already same, please return a false. Just stating false means, okay, they are already union, so you do not have to specifically union them again. It is just a code. It's your wish. You have to write that in not, like, or not. It's just representing that, okay, it says it is already unioned or not. although you can also handle that as an if condition in your code itself, but it's just a code or a snippet which I use for my case. Cool. Now what if I want to union them, which means B and F both have a parent A and E. So now I will union them. Again, for union, you will go and ask the rank. What you will see is, okay, rank of this particular component is actually a 4. Rank of this actually a 2. So I know rank is more, rank is less. So for sure, it should become the parent and it should become the child. Now, as I'll go and ask, if the rank of X set, which means if the rank of X is less, so for sure, whosoever rank is less will become the child. So X will become the child and his parent will become the Y. But if the rank of X is more or equal, then for sure, Y's parent will become the X. Here in this case also, my rank of X was more. So my Y's parent became X. So my Y's parent became X. That's the same thing. My Y's parent will become X. And as my Y's parent become X, what I need to do is simply go and asking, okay, and for sure, if this parent has become X, so it will just go and attach, okay, now my parent has become this, but simply again go and find out, okay, rank, for sure, again, the rank is same. When I will go and find, the rank will actually be this one. But if let's say both of them are of the same rank, then what to do for the rank stuff? Nothing. Simply going and finding out if the rank is the same of both of them, for sure, which means X set and Y set rank were same. So simply go and say, firstly assigning the parent of Y as X, but rank was same, which means both were same. You assigned Y's parent as X, so X is on top, Y is at the bottom. Rank of X has increased, so simply increase the rank so as to know, okay, now Y and X are actually different and the rank of X is more now because Y is now the parent. So I just simply increase my rank of X, saying my rank of X has increased, and just increasing that rank by 1, say, okay, if both of them have the same rank, so for sure the rank of one will actually increase. But if they're already increased, which means if they're already different, for sure the rank will already be more than the other rank. Cool. Now I have done and return a true so as to know, okay, now if you have actually unioned them, it was already not in the same component. That is how our DSU will work. I know I spent a lot of time in actual union, but I wanted to explain the union very specifically because of this snippet code. That's the reason, like many people write union in a different way, but I want you to follow your one union code. If you have yours, then it's very good. Now coming on back to Kruskals, in the Kruskals I showed you, I have my N, I have my edges, and I have my exclude and include as well. Exclude will say me if I want to exclude an edge, include will say me if I have to include an edge. Again, I will go and initialize my DSU. As I showed you in the code, weight will actually be the MST weight. And firstly, as I showed you, if I will include an edge, so I will pass an edge E to actually include. If I say, okay, if that include an edge is not equal to -1, which means I have to include an edge, which means if I want to include an edge, please, firstly, include this edge. Firstly, initially, every node is different right now. Nothing is made, no tree is made. So include this edge. Just add this particular weight in your weight, add this particular weight of this edge in your weight sum, and just simply union this, which means just simply A and B have this weight, have this weight. It was added in the weight, which I have MST weight, and I just did a union of these two edges so as to, okay, now, okay, I have just used this particular edge. Now I will go on to every edge, but make sure this every edge I'm going on in the ascending order. And how I know that? Because in my code itself, I just initially sorted my edges on the basis of their weights, which means I have sorted the edges on the basis of their weights, and the edges are now in the ascending order of their weights. And also in my main function, I have already pushed in the indexes because I know I have to actually push in back in my critical and the pseudo-critical vectors, which I have to return in the end. I have to push in the vectors, which means I have to push in the indexes. So you will see I will push in the indexes. I will push in the indexes and not the actual values. So it's the reason I just pushed in the indexes itself. Now coming on back to the Kruskals code, again, I will just go and say, if for that particular node, if I had to exclude that node, so simply continue it, which means you cannot use that in your Kruskals code. Continue it. But if not, then I'll go and find, okay, the edge is this particular edge. It is my edge. but I want to know if they are in the same component or different. So I'll go and find, I'll do a find. If the find have, okay, this find will give me the parent of node A, it will give me the parent of node B. If the parents are same, which means for sure they are in the same component. So continue. Please don't put this edge, because Kruskals will not affect by this particular edge. It will make a graph and not a tree. So I just don't want that edge, simply skip it. But if it is not, which means if they both are in the different components, simply do a union. Now if you do a union, it's just to show, okay, now they are in the same component, but I'm concerned more on the weights end. So I'll just simply add that in my MST weight, because I am concerned about the weights of that particular MST. I'll keep on going it for every edge in the ascending order of the weights. Ultimately, in the end, I can simply return the weights. Although for your generic piece of code, you need to know that, okay, if here in the problem you are specifically mentioned it's a connected graph, but not every time your graph is connected. So in that case, you need to know if your tree, which means the MST, minimum spanning tree, if your tree itself cannot be formed, so you need to know that you need to return a 1E9% or a maximum value, so as to know, okay, for sure your tree cannot be formed. For sure your tree cannot be formed, which means your MST, your minimum weight is not minimum anymore. It will be an infinite or the maximum weight if your tree itself cannot be formed. So that's a code, although it is not required for this case, but it's a generic piece of code which you can have it in your interview, because interview you have no of such conditions. Okay, let's say I just see you, okay, it's not important to have a graph as entirely connected. It can be an maybe he never mentions about this fact, so you need to put this condition, because else it will give a wrong answer. Now you have find the MST. How to find the MST? You have used a DSU. Now everything is done. Coming on back to the main code. Firstly, you know that I pushed on the indexes. I also sorted all the edges on the basis of their weights itself. Now I will go and find the original MST, because that is the one thing which I will compare after including every edge. I'll compare this with the original MST. So I'll go and find the original MST. Like while saying, okay, I will just get the original MST by simply ignoring include, exclude. I will simply ignore it, and I go and find the MST of the simple n and edges. Now I have the original MST. I ultimately want to know the critical nodes and the non-critical nodes, which means the pseudo-critical nodes. I'll go on to every edge, try to exclude every edge. So I will firstly exclude every edge, which means I will go and find the MST weight. If it is more than the original MST, excluding that edge hampered me a lot. So I will say, okay, excluding an edge increase my MST weight, so for sure push that in a critical vector. But if it is still same, which means if the weight remains same, I'll go and say now include this edge, and go and find if it is equal to original MST, it's a pseudo-critical edge. So I checked for excluding it. If excluding it hampered me, okay, it's a critical edge. But if excluding it did not hamper me, I'll try to include it. And if it still did not hamper me, okay, it's a pseudo-critical edge. And ultimately, I can just return the critical and pseudo-critical edge. Although, you know, and still you know that time is O of E square log V and space is O of E plus V. That's how you can simplify. Code is down below for your reference. I hope that you guys the video, it went very long, but still I want to explain everything entirely, DSU, MST, and this problem itself. Cool. Bye.